Hello, friends. Welcome to Science Talk. I am your host and resident oceanographer, Jim Massett. I'm going to share with you an abstract from a paper that's just been accepted for publication. It's still going through all the proofreading, pagination, typesetting, editing, etc., etc. But I wanted to share this with you because of some of the interesting implications of this research here. As you can see here in the title, distinct ocean responses to Greenland's liquid runoff and iceberg melt. And the authors are Juliana Marson, Laura Gillard, and Paul G. Myers. So, what are they saying here? While Greenland discharge has been increasing in the last decades, its impact on the meridional overturning circulation, MOC, is not clearly established. Because of that, the accuracy of this discharge representation in ocean models has not been a priority in large-scale circulation studies. So they're basically trying to address that a bit of a deficiency, if you will, and to at least get a better handle on things to improve the models. Many models prescribe Greenland discharge solely as liquid runoff from the coast, even though around half of this mass loss is attributed to solid discharge, i.e. icebergs. When the ice calves and you have ice. So not just liquid coming off Greenland, but ice as well. In the study, we used sensitivity experiments carried out with the nucleus for European modeling of the ocean general circulation model to show the most relevant impacts that different Greenland solid discharge parameterizations, transforming to liquid runoff or explicitly representing it through an iceberg model, have on the western subpolar and Atlantic. We find that icebergs act as freshwater reservoirs that affect how much, when, and where. This is the key part of this whole thing. Where freshwater is delivered to the ocean. They carry large amounts of freshwater away from boundary currents, releasing it in the interior of the subpolar gyre. Moreover, the amount and variability of freshwater delivered to the ocean depend not only on the characteristics of Greenland discharge itself, but also on the environmental conditions icebergs are subjected to. We also find a large difference in subsurface temperatures in the Gulf of St. Lawrence, which suggests that different Greenland discharge parameterizations might have far-reaching implications beyond the MOC. Although differences in ocean fields between the simulations are usually small and within their interannual variability, they might be relevant as Greenland calving rates increase with global warming. Now let's look at the plain language summary. The Greenland ice sheet is one of the main contributors to sea level rise since it has been discharging an increasing amount of water, melt, and icebergs, to the ocean in the last decades. Scientists that use numerical models to study the ocean's circulation and climate often represent Greenland's discharge solely in liquid form, melt, when in reality about half of it appears in the solid form, icebergs. In this study, we investigate how this approach, assuming all of Greenland's discharge is liquid water, differs from representing the solid discharge as icebergs in terms of effect on the ocean physical properties. Results show that while most ocean responses between the two approaches are only slightly different, icebergs change how much, where, and how much, when, and where meltwater enters the ocean. We also show that this distinct delivery of meltwater can affect the ocean circulation, which might have consequences for the ecosystems that depend on it. Okay, so let's kind of do a recap here, or kind of, and look at the implications. Right now, we know that we have fresh water pouring into the Arctic Ocean. We're losing the sea ice, right? So we have all this fresh water building up in the Arctic Ocean. One of the questions that remains is, what happens to that fresh water? Is it constrained within the Arctic Ocean basin, or is it pushed out, for example, through the Fram Strait into the North Atlantic, where it will then meet up with the Greenland ice melt, the water, putting that freshwater lens in the ocean surface, which then slows down the vertical sinking, slows down the MOC. So that's so we know about that mechanism. But now what they're saying is, all the stuff that comes off Greenland is not necessarily liquid water. Some of it is in the form of ice. And what they're basically saying is, our understanding of the ice needs to be improved. Therefore, they want to know, what happens to the ice? Where is it transported to? And at what point does it melt? And where it melts, how does that affect the situation? The environment, the local environment, the overall environment, the overall ecosystem. So let's say, for example, some of that, the iceberg does not melt in the immediate vicinity because water temperatures are perhaps too cool. Okay, it's going to be transported further south. Maybe it gets transported to 50 or 40 degree latitude. Say by 45-degree latitude, might start melting there. So now, how does that meltwater affect what goes on? And of course, much of it depends on how much mass, how much volume of ice ends up and where it ends up. If it is a small amount of ice and it melts, then any freshwater input will probably not be of great consequence. But if there's a lot of ice and a lot of it gets transported into a specific local area where those icebergs then melt, it's very possible that they could contribute a not insignificant amount of liquid water that could affect, vertical movement of the water. But here's another thing to think about. What if enough icebergs are carried away from the Jin Sea, basically, where the typical overturning takes place? And what if the fresh water in the Arctic Ocean is constrained within the Arctic Ocean? As you look at the conditions of the Arctic dipole, and it's such that the water is not ejected out into the North Atlantic. Then the surface dilution while it still be occurring, could very well be not sufficient enough to stop or severely slow down MOC. So you can kind of see the different possible scenarios that could play out. So this is an important question as to, where does the ice go? How much of the volume is it? And when it does eventually melt, how does that affect the overall physics of things? So it's very easy to say, okay, liquid water, we're slowing down MOC, and the deep water flow is slowing down and that sort of stuff. Well, maybe now, if we have if the ice were to say melt right in the Jin Sea, okay, sure, that'll add and contribute to the freshwater land and really further make the slowdown worse. In other words, really the slowdown increases. Kind of oxymoronic. We're slowing down, but the slowing is increasing. But you know what I'm saying. The rate of the slowdown will go faster. So that's This is going to be interesting to see what they say in the paper and how they assess it. But this is something that does need to, we need to improve our knowledge here. And basically that will help with the modeling. And we need to see what this does, the distribution, the volume, and where it melts. And, if it melts, okay, it may be insignificant to affect the physics, or it could be significant enough that the physics does get changed. So this is another aspect to part of this whole complicated system called planet Earth. And it is interesting that this aspect of what the ice coming off Greenland, its effect, its influence, has not been fully studied yet. So its understanding of its role is incomplete. And this study, I think, would most likely going to be a first step to improving our knowledge of that. So stay tuned. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.